diagram from Simmons et al. 2005 showing the major components of low sulfidation systems. These are meteoric water dominated, so largely the water table, so 90-95%. That in the shallow surface, and that's what he shows with this volcanic rock package up top. Then faults are controlling the permeability in this near surface environment. And when I was thinking about this project and how to kind of framework it, I'm putting the different components to understanding low sulfidation deposits into this model by McCrae and Ronsky of a self-organizing critical system for this hydrothermal ore deposit system. And everything in the shallow surface environment is really the energy sink for this system. And this is what's been studied at length historically, going all the way back to Lindgren, looking at the alteration assemblages and geometries of the surface, as well as the veining geometries and textures. And the other kind of focus of research has been this energy source, the magma source for fluids and metals. A lot of work's been done here looking at isotopes, fluid inclusions. But the component of the system that's been overlooked, maybe not overlooked, it's just really hard to put your finger on because it's transient in existence and poorly recorded in the geologic record, is the geologic barrier. What is separating these two portions of the system, and how is that being overcome in very discrete intervals to create these deposits? This is what they describe as a threshold barrier. And there's very short time periods that barrier is broken, and you create a very focused system that allows the source, being this magmatic source of depth, to interact with the shallow environment to form these deposits. And that was kind of the focus of this research, is try to understand what's going on during these transient events. And to do that on multiple scales, starting at the very largest kind of rift scale and working our way down to individual deposits and veins, and trying to establish what this link is, what this barrier is being overcome. So those not as familiar with Nevada, here's kind of a brief overview of the project. On the right is just a Google Earth kind of image map going from Utah over here on the right. Nevada is kind of the center portion of the map. California, down the north is Oregon and Idaho. And anybody that's familiar with kind of the Great Basin, it's very prevalent in epithermal deposits. Not only epithermal deposits, and that's all of these little balloons you see on the screen, but mid-Miocene age ones, the purple ones. And they're not homogeneously dispersed. You see they're kind of localized. The majority of them are localized with this feature called the Northern Nevada Rift. Named a rift, many can argue if it actually is one or was one. But this is really just the southern leg of the larger Columbia River flood basalt, large igneous province up here to the north. And this is just a large tectonomagmatic trough that extends through the southern or central portion of the state. And our kind of main observation is exactly this, that there's 15 epithermal deposits along this rift, and they all formed within 1 million years of each other. And that's not by coincidence. There's some very critical series of events and structural controls and geologic controls influencing the formation of that number of deposits in that small area in a very short time window. And what are those critical processes? Our ultimate goal was to identify and establish relationships between those processes, something that's much easier said than done when working with an incomplete geologic record. We felt we had a pretty good chance with the number of deposits here. And at the time, the company was trying to incorporate our understanding of multiple systems that they had acquired to kind of understand the greater context of the rift. So having an abundance of data. And this was checking two boxes. This is trying to help develop a systematic exploration tool for industry, as well as academically understanding this gap in knowledge of what's allowing the shallow environment to interact with the deep magmatic environment. So just for reference, I-80 is kind of tough to see. There's a yellow line coming across. This is the highway going from Salt Lake City over to San Francisco. Passes by Elko right here where the cursor is. And once it gets into this region, you're approaching Battle Mountain. And our project area is pretty much I-80 corridor south all the way to the town of Eureka down here. So it's a fairly large area that we worked and mapped, but we felt it was important to really understand a much larger system controlling these very postage stamp size epithermal deposits. And I might get ahead of the slides. So of course, if I'm way ahead, I'm not sure how bad the technology lag is, let me know. We're now on a map of north central Nevada. Very basic geology is overlaid. The main feature to point out is volcanics, tertiary volcanics, the kind of browns and oranges. The Paleozoic basement is the kind of pinks and purples. Northern Nevada Rift, you kind of see its footprint marked by this finger of brown, largely mafics, but then rhyolites up here in the north, extending all the way down through central Nevada. The most enigmatic feature of the Northern Nevada Rift, suggesting it's really a crustal scale structure, is the magnetic footprint of this system. It's quite large and distinct when we look at aeromag across Nevada. And that's really being a feature of, this is a crustal scale structure, a large emplacement of mafic magma into the crust occurred during the mid-Miocene.
Oh.
And
Oh, sure.
Yeah.
bullet point to that. That mafic magma has made its way to the surface in discrete locations and been preserved as pockets of superficial basalt flows that were kind of capping basin filling sediments in a series of basins along the axis of the rift. In the southern portion, these are segmented basins. They weren't completely all connected, and each one of these mountain ranges has kind of a preserved basin that allows us to kind of make observation interpretations about the basin geometry. So as we flew in right here, we're looking now at the Roberts Mountains and kind of basin stratigraphy is over here on the left. Going, as you can see, from late Eocene basin fill, and these are gravels, lacustrine sediments and tophaceous sediments, then up through a Miocene package, which are largely browns. Basalts at first, then it evolves into more felsic components of dacite, then back to basalt. Then the key up here to the left are the series of age dates, both previous ages, then 58 new age dates by us as we move through these map areas. And this large footprint of fieldwork has allowed us to kind of develop this time scale of major events in the Northern Nevada Rift. So I might get ahead, but we're going to fly through the different field areas. Roberts Mountain is unique, and we'll revisit this because it's been highly exhumed since the mid-Miocene. It's kind of if you haven't been there, it's a neat area to check out. There's little glacial cirques at the top of the range. And on the back slope, we're now looking to the south. You have discrete pockets of that Miocene basin still preserved that give us a proxy for the Miocene paleosurface. As you move north on the range up to the Quaternary basin bounding faults, right here, you're almost moving 2 kilometers beneath the Miocene paleosurface into the structure that was controlling that basin. As you can see by the dike swarm, highly exploited by Miocene age basalt dikes. And this allows us to make some interpretations and calculations what was controlling this basin. Oh, shoot. Technical glitch, guys. We're going to go right back through this little video real quick. The next, moving north in this range, we're going to go to the Simpson Park range. There's another map area we did to the north, and what we really focused on was mapping these tertiary basins. And I compiled these maps with the same volcanic units, correlated volcanic units, so we had a very consistent story along all 4 mountain ranges. Then use previous mapping for all the surrounding Paleozoic bedrock. So it's not all brand new mapping, but all first time compiled. So that's the Simpson Park range up north to the Cortez range that we're looking at now. Those familiar, this is also host to one of the larger endowments of Carlin style gold in the world, the Cortez Hills property here, pipeline. Then the new Gold Rush 4 Mile is actually underneath the edge of the Miocene Basin. This is one of the more exciting geologic laboratories to work because there is a very well preserved Miocene paleosurface here, a number of center terraces on top of these basalts. And if we move to the north, again, down to the Quaternary basin bounding fault, we're moving almost a kilometer into the subsurface beneath that Miocene paleosurface. The largest basin that we worked on is in the Shoshone Range. I-80, you can see right here on the top of the map, goes off to Battle Mountain Airport right here. This is also host to two larger epithermal deposits in this portion of the rift. Fire Creek, which is now operated and owned by Hecla, is right here on the Malpine Rim. Then the Argenta Rim is the one that you would see if you drive by I-80, hosts Mule Canyon, which is the little yellow balloon here, which was operated by Newmont in the 90s and early 2000s. Both roughly 1 million to 2 million ounce endowment. The nice thing with this exposure is we have two kind of escarpments that allow 3D exposure of the basin, both east to west and north to south. So we can really unravel the development of this basin with relation to the deposits. And similar story here, where we actually see beneath the Miocene basin into the subsurface. Paleozoics, where Miocene basalts were ascending up to feed both sills and these lava flows. And the real key takeaway here is these blue lines represent mappable normal faults, and you can see the significant thickness of the Miocene package exposed here on this escarpment. This is being really accommodated for by slip, coeval slip on these normal faults, creating this accommodation space that's being recorded by these relatively low viscosity basalt lava flows, quite literally very small flood basalts. And that record of growth faults and datable basin filling materials allows us to kind of get a time-space history of slip on these faults and relate that back to basin evolution. And that's kind of the focus of the large scale of this study. And ultimately, the rift kind of has a much longer story than it's given credit for. Magmatism we have extending for almost 5 million years. Volcanism is a little bit shorter lived, especially depending on what basin you're in, but in this basin, roughly 2 million years. Then we see, if we look at separation of flow contacts on the volcanic units, active tectonism associated with the mid-Miocene only lasts for about 1 million years. And there's a very short time window during that tectonism that you have mineralization, as far as we can absolute age data occurring, roughly 100 to a couple 100,000 years, depending if you're looking at absolute or relative age dates. So it's a very abbreviated story when you're looking at hydrothermal activity related to deposits with respect to the whole rift. And all that can be summed up in this slide. We have our major kind of geologic processes going left to right: magmatism, volcanism, tectonism, and hydrothermal activity, then time on the y-axis. And it wasn't one of our goals outside of this onset of this project, but mapping all of these Miocene basalts, you eventually work your way off Miocene volcanics, keep working down slope, and it's a while before you get to Paleozoic basement. And what we identified, sorry, my dog in the background, identify was underneath all these Miocene volcanics is an older basin. And from where we can get cross relationships with datable material suggests it was late Eocene onset of extension. And this is something that's been also observed in the Southern Carlin Trend with a fellow PhD student of mine, Elizabeth Hollingsworth at UNR, is that you have much more widespread establishment of late Eocene basins in Nevada than kind of previously thought. And that's significant because on the east and western edges of the Northern Nevada Rift are large trends of Carlin-style mineralization. And unique thing about the southern portion of the rift, a lot of the faults that host Miocene mineralization on their shallowest components host Eocene age Carlin-style mineralization down dip, the reactivated structures. And that's, I think it's one of the requests I've gotten the most is for a copy of this kind of block diagram I'm about to show. What this block diagram is illustrating is the Paleozoic basement is in purple, kind of a schematic Roberts Mountain thrust. And here are these growth faults developing through time. And this orange represents the basin fill material during the Eocene. And this is kind of captured in this diagram where subsidence rate is a factor of time and time decreasing to younger on the right. And what we're seeing is really the Northern Nevada Rift, the southern component, is really a story of ongoing structural development of extensional basins going from the late Eocene, a large hiatus in the Oligocene where we really don't see much going on. Then in the mid-Miocene at roughly 18 MA, it's believed that the thermal weakening related to the migrating plume head of the Yellowstone hotspot caused or triggered the gravitational collapse in Nevada Plano. And these faults that had already been established become reactivated and rapidly slip for about 1 million years. And that's what this block diagram is attempting to illustrate. It's these same faults that become reactivated, the Miocene, propagate up into younger basin fill, largely mafic volcanics, and it's up at the upper components of these growth faults where we're hosting Miocene age epithermal mineralization. And the best place that we can really visualize this and see it is in that northern basin, the Shoshone Range. So this is a kind of a schematic fence diagram using strat sections going from west to east across the map area, so A to G. And the next cross section goes through the center portion of the basin. The next series of strat columns is on the southern. And you can see our real goal here was to correlate the volcanic stratigraphy across the basin to indicate that this is a very systematic series of lava flows that are filling in this depot center. Now I'm going to highlight just the major contacts. The blue line is marking the unconformity between the Paleozoics and the Tertiary. So that's really the bottom of this basin, which is Eocene to Miocene in age. The top of the Eocene with the contact of the Miocene. Then the top of our main host rock for veins and epithermalization in the basin is the red line. Mineralization occurs a very short time window in a very discrete structural setting across the basin. I didn't point it out, but the black lines between the strat columns represent the major northwest-oriented normal faults that are accommodating basin subsidence. And you can see those faults are really creating a deep trough in the center of this basin, coming right up here where the cursor is, or these center strat columns on the diagram. And the deposits are forming the medial footwall to that high displacement fault. And they occur in a very short time interval during that basin development. This really gives us a good picture that we have a large, relatively deep basin forming in a short time frame. And the kind of thing that I've gotten from a lot of people talking about this, it's hard to see this when you're out in the fields. And that's largely, these are growth faults, and they almost have zero displacement at the surface. You have one flow, you can walk from across to the other with almost seemingly no displacement. And you're just walking on the lowest slip portion of that fault, its uppermost component. To really see the displacement, you have to go deeper down in the basin. And that's what we're going to look at here. So this is the geologic map of the Shoshone Range. We're going to look at section A to A prime, going from west to east. We used kinematic modeling, so modeling of the basin through time through a software package called Midland Valley's Move software. And I think the company name has changed, but the software is the same. Done is taking the 13 major basin forming faults across this cross section, going from pink to red, west to east, numbered here. What we've done is taken the flow contacts on either side as pierce points and calculated the throw and heave across those faults given time period based on the basin filling unit to kind of calculate a rough throw history of each structure through time. And this is really a good way of kind of estimating where the strain is being partitioned in the basin and how that basin is evolving through time. So those 13 faults going across the basin are going to be represented on this diagram here in the bottom left. Time is on the x-axis, going from oldest to youngest, left to right, then cumulative throw on the y-axis. And it's Simplistic looking at it, but powerful in what that data is telling you as far as the basin development. What you're seeing is very few faults are really accommodating the majority of substance of this basin. And which faults matter a lot to where you're going to form a deposit. What we're really seeing is strain is focused on the western margin, median, and as the basin develops over the mid-Miocene, the western bounding faults become inactive, they probably become inefficient, and strain moves east. And it's during that migration of strain eastward over to the eastern margin of the basin, going from kind of a half graben to full graben geometry, that deposits are forming where that yellow star is. And it's right in the medial footwall of that blue fault, the mule shoe fault. And the best way to kind of visualize that, I'm not a Pixar animator by any means, are these simple animations to kind of visualize what's going on through the developmental history of the structural basin. The real thing here is that as strain is being partitioned from the GMC faults over the mule shoe fault, you're really creating a lot of co-seismic permeability as all these antithetic faults and fabric within this block. And really, this is a fault-bound block. So it's really a horse block, or I call it a rider block. You're creating short-lived permeability when all the strain is focused here, hydrothermal fluids and magma. Sorry, my dog has to join me. He gets on the paper. And hydrothermal fluids and magma are short-circuiting their pathway up across that block to what I call the apex region. And that's the location you find epithermal deposits along all four of these basins, north to south. They are exposed and exhumed at that location. So unique location based on the actual development of this extensional basin. And from this model, we're able to calculate the total extension as accommodated for by faulting across the basin, and only 4% extension. So we're really supporting a lot of previous researchers' suggestions that the Northern Nevada Rift isn't a very good rift because it's not that significant of an extensional basin. But I think this, you'll see this undersells it. We're just calculating extension based purely on heave alone. What we're discounting is how much extension is being accommodated for by magma injection into the crust. And then we'll see that's quite significant. We alluded to it by looking at those dike swarms in the Roberts Mountains. So that's where we're going to next. And just reference, going to step back. The fun thing here is we don't only have one geologic laboratory up here in the Shawnee Range. We have those other map areas to the south. So what we identified through this study was this rider block in the central graben region are where we're having most of the strain being focused during the Northern Nevada Rift. It's fairly intuitive, but we have very poor exposure of these regions in this area. We move to the south, we can understand this rider block region and the central graben much better from exposures in the Cortez Range, the Roberts Mountains Range. So these maps we're looking at now are just little thumbnail components of those larger regional maps of the whole mountain range. Roberts Mountains on the left, this is the very northern escarpment. The Q fault is right here, bounding Paleozoic Basin next to the Quaternary Basin. Same thing here in the Cortez Mountains. Quaternary fault bounding the Cortez escarpment next to the Crescent Valley Basin. What we did here was use these dikes as proxies for dilation opening and aperture opening of structures that we get tied to faults, base mounting faults of the surface. So it's kind of a gross approximation, but we can use the dikes and the widths of dikes to kind of approximate extension or change of permeability, which is really kind of a more gross assumption. But what we're able to see is at different depths beneath the Miocene paleosurface, we have a order of magnitude greater amount of extension occurring in these structural corridors. In the Roberts Mountains, that is in the rider block, we almost have 26 to 21% extension occurring in a very discrete block across the rift. Same thing in the Roberts or the Cortez Range. This is more or less the whole central graben in the basin there, and we have about 30% extension in the immediate subsurface. So what's really showing us is across the whole Great Basin, strains being focused along the axis of the Northern Meadow Rift, allowing magma to come up to the mid-crust to give us the aeromag anomaly. Then strain is being focused even in a tighter window in this kind of epithermal environment, the upper 1 to 2 kilometers, in the very discrete margins of the basins that is allowing permeability pathways to form to both enable magma to get to the surface to feed the flows and the hydrothermal fluid. So it's really about strain partitioning across the whole region. It's all being focused in very narrow corridors. And we zoom in a little bit more to the next step. We look at Fire Creek, at the deposit area itself. Fire Creek underground epithermal mine. And just for reference, this is up again the Shoshone Range. The Mule Shoe Fault was that blue fault in our large A to A prime cross sections right here. To the east of that is the main central graben. So a significant slip in this fault, displacement down dropping about 1 kilometer, that central graben. Then the deposit itself is here. The red lines are veins projected up to surface. Only 1 or 2 veins actually make their way to the surface. You can see some of the mine workings down here and underneath on the base map. What we did here is a very similar study to what we did up in the Shoshone Range. We took a cross section through the deposit area from where the known mineralization is. In the cross section, west-east, A to A prime, Paleozoic basement is largely undifferentiated. Very few holes actually go into the Paleozoic basement. Then the TS, the orange, is our Miocene sediments. This is lacustrine sediments, volcanics, ash flow tuffs. Then the brown is our Miocene package. Dark brown is basalts, basalts again in TBA, the basaltic andesites in THH. The red are dikes or sills on the cross section. Sorry, slight different color code than the map. The veins on this cross section are yellow. And the major takeaway here is there is twice as many faults or major faults in the cross section as you actually cross in the map. And that's due to the fact that most of the faulting occurred in the very early stage of basin development and failed to continue slipping through the later stages. So most of these growth faults die out by the time you get to the THH package. We're able to kind of put some time frame on this by a large suite of age dating we did at Fire Creek, not only on the veins. We did, I think, 12 age dates on veins, and almost all the age dates come back in this roughly 100,000 year time window from 16 to 15.9. That's corroborated by age dates on the overlying basalts and host basalts as the same time window for cross-cutting relationships. We're able to take the absolute age dates and the faults, then again taking flow contacts across each structure to calculate cumulative through time on these faults in the deposit area. We see a very similar story here, albeit just to this individual deposit that we saw in Argenta Rim. Very short-lived fault activity. It kind of reaches its maximum rate at the end of the first basalt package, TMC. And that's the same time window that the hydrothermal activity is occurring, the deposits are forming. Not only that, but more or less the green faults, which fault 3 on this cross section, also associated with the kind of Vani vein, highest displacement fault, so highest slip rate, is also, if you interpret it this way, the main primary feeder for the whole epithermal system. All the antithetic, majority of the antithetic fault veins on the hanging wall side project and dip into it. Same thing with the synthetic ones, and the drilling corroborates that. Then kind of another neat takeaway from doing this calculation is we also get a number for the degree of extension across this little apex region of the Rider block. And this is unique in that we're not taking into account any of the extension or heave that we measured on the major basin forming faults. So the thick blue line is something you map on 1/24,000 scale. You would have a tough time picking out these little small displacement faults at that scale. we calculated 4% extension on those large faults. We're not taking into account, if you look at all these smaller faults that are very subtle in their growth faults, most of them go to zero displacement towards the upper lava flows. There's 20% extension occurring just on these small displacement faults. So we're really, again, showing this record of focused strain into that rider block on the western margin of the basin. And that the 4% extension is really underselling how rapidly this basin subsided and extended during the mid-Miocene. So let's really appreciate the syntectonic feature component of this research and trying to tie active faulting to deposit formation. We did a kind of detailed model on Fire Creek. So it's that same cross section, everything in that green box. We created a volume using Midland Valley's MOVE software and did forward modeling this time. So what we did, we took the actual rock characteristics, approximate thicknesses, put it into 3D volume. That's where you're looking over here on the right. And what we did was put the very early geometries of the Vani faults, that main fault that we identified through our kinematic model, into this volume. And what our goal is to model the growth of this fault through the mid-Miocene. And the real hypothesis is the fault and the fault development is creating the permeability that's triggering the release of fluids into this environment. And if that's the case, the faulting should come before the epithermal veining, and that it's not hydrothermal boiling and eruptions that are causing the permeability. And this test, this forward model should create the similar geometries we see in the real world. So how we capture that is, you see the teal strain ellipses on the volume. That has a 2D plane that's going to capture how strain is being partitioned off this propagating fault tip into the surrounding volume. And one of the applications in the MOVE software is using this tri-shear algorithm, because I am not a mathematician by any means, to model how the propagating fault tip is imparting strain in the surrounding rock volume. And we're not really predicting rocks breaking. We're just kind of qualitatively showing where strain is going and how it's being partitioned through time and successive fault ruptures. So we're going to skip a lot of the details and just look at the final product. This is the 2D plane of the strain ellipses through that volume. What we did, we took that fault tip where it would have been the beginning of the mid-Miocene above the TS sediments and propagated up through multiple earthquakes and fault ruptures. Now I'm just highlighting the upper portion of the TMC basalt package, and that's the host of majority of veins at Fire Creek. And highlighting the deformed strain ellipses there. And what we're seeing is this growth fault is critically important in the vertical propagation of permeability. And largely it's going into the hanging wall side where you have less confining stress and you're creating these antithetic high strain zones, which inherently, if there's enough accumulated slip, you're actually going to create faults that are going to propagate up on the hanging wall side. And this is really mimicking the geometry you see in these deposits, this vein swarm and stockworks, suggesting it's critically tied to growth fault propagation. Now, another neat feature this model predicted, is where that fault tip is not been displaced enough to create a dislocation surface, you're actually getting this fault propagation fold. And this is something we subsequently identified in the field along strike. As we moved higher up in the section, you're actually seeing large, broad folds over these developing faults. And other takeaways from this is you're getting slip partitioning onto the hanging wall structures. And we see in the veins themselves, you're actually kind of getting hydrologic partitioning. If you got fluids moving up a feeder structure, they can't in place on a vein that hasn't formed yet, or an antithetic zone that hasn't formed yet, if the fault tip is down deeper. So the first antithetics have the chance to not only accumulate the most slip, but arguably more hydrothermal activity and fluids moving up from them. So the next story we're trying to tie into this is how the basin development is not only influencing the hydrothermal activity, but we identified a lot of the volcanic vents were co-spatial with mineralization. And we had a very similar or simple understanding of Fire Creek when we started here, of being the earliest lava flows, and very near the end of that lava sequence, this last fault ruptured, created permeability, fluids came up, formed veins in the hanging wall side. While going back to the core, relogging and remodeling this, and the difficult thing is everything's basalt, so it's really hard separating out different basalt flows from one another in core and basalt dikes. But we're able to kind of form this picture from that same cross section. And what we're seeing is that final rupture of the TMC package triggered the incursion of dikes into what I call kind of this bathtub area, and evacuated out more or less this large trough that is best visualized by this dark brown unit, which we call a TMC with enclaves. What that is more or less a turbulent lava lake, and the enclaves are all different class and fragments of older units deeper down in the section. And some of the largest class are large rafts, to be honest, of tough material, which is portions of the TS, underlying TS, are caught up in this turbulent lava body that actually flowed out to the west. And we've seen similar geometries at Mule Canyon and other locations in the rift. So there's a very close time-space relationship between fault ruptures, magma incursion. As you can see, shortly thereafter, the veins are bright yellow, are following the same structural pathways up into this volcanic feature. The main takeaway is, if you bring this picture back to the regional framework, this cross-section of Fire Creek and the main zone of Fire Creek deposit sit right here at the apex of this footwall block, the margin of the rift. This Vani fault is really the highest displacement antithetic structure that comes down. And we've done other structural modeling, geometry modeling, and likely sols into the GMC fault. And that's really our highest displacement fault. So what this suggests in this cartoon model is that really critical events that allowed Fire Creek and Mule Canyon to form at roughly the same time came from the dual rupture of these larger basin forming structures, the GMC and Mule Shoe fault. And through this kind of cartoon, trying to visualize that. These faults have a significant enough strike dimensions and down dip dimensions to cause surface rupturing normal fault earthquakes, kind of magnitude 7 and above. And one can argue that one of these critical events bridged this gap both figuratively and geologically between the surface environment and some mid to upper crustal magma chamber, allowing the incursion of magma up here to feed this volcanic event, as well as interaction with that meteoric water table to cause a free automatic eruption and subsequent hydrothermal fluids coming up the same structural pathway to form the deposit. It was really the important event is the basin forming faults reached dimensions capable enough to bridge that gap. And when they did that, the shortest path of least resistance to the surface brings those fluids and that magma to that apex location. As we mentioned in the previous slide, not only causing slip partitioning across these suborder structures, but probably hydrothermal partitioning on these ascent pathways. And the fun part of the project is we keep shrinking in scale, but we see the same relationships between hydrothermal events and tectonic events. So I think Corey mentioned it. I did actually do ore control here and help out with initial mining. So I spent quite a bit of time underground, which I do enjoy being underground. So I became intimately familiar with some of the relationships, the unique features you see of these veins that don't make it into textbooks all the time. So this is a phase photo I took when doing ore control. On the right is the rib where the bolts are. Then the face starts kind of right here where the shadow is moving to the left. And we can see this isn't your textbook picture of an epithermal vein. It's not that pretty. It's not a big banded vein right in the middle. It's actually a series of synthetic little veins coming into the footwall side of the main slip. The main slip is this surface here where the larger vein is. And these are all little like right L shears coming off the main slip surface. And I'm going to highlight one of them because a lot of these are very low displacement, but they do have displacement. They actually cause separation of that vein wall rock contact, and it's actually down dropping, creating an accommodation space for those hydrothermal minerals to precipitate out, which allows us a very unique opportunity if you're looking for these things. And trust me, I wasn't doing this when I was doing ore control, but you just see these relationships. When I came back to the research project, tried to capture them. But you have the opportunity to capture syntectonic fabrics preserved in these vein conduits. And that's what we're looking at in the sample here in the top right. So this is from the Weiwu vein. The wall rock contact, the oldest portion of this banded vein, is at the bottom of the photo. Then the vein youngs going up. You're moving towards the center of that conduit. Where these little micro slips intersect, you're actually creating growth-like geometries along these micro faults that are incrementally displacing these banded veins, or the banded portions of the vein. That's beautiful. In a geologic perspective, it's also beautiful in the fact that we have adularia, potassium-bearing feldspar, and we can date these individual bands. And in a good way and a bad way, the Fire Creek deposit isn't a huge epithermal deposit, which is bad for investors mining it, but good academically in that the system shut off relatively quickly enough that you didn't have significant argon loss on the older bands. So we're getting statistically significant age separation from the oldest and the youngest bands without argon loss. That allows us to constrain the time frame of the whole banding sequence in the veins at Fire Creek. And what you can see is there's roughly 100,000 year time window from the oldest to the youngest bands. On average, this occurs over 5 different intervals of banding, which suggests to us that there's roughly a 20,000 year recurrence interval. And this was a fact not pointed out to me, but one of my committee members, is that's more or less the average recurrence interval of large surface rupturing normal fault earthquakes across the Great Basin. So the actual systematics of extensional tectonics hasn't changed much since the mid-Miocene, indicating to us that even though these are small slip events preserved here, this is intimately tied to slip and rupture of the basin forming faults. And this is just little micro earthquakes being preserved here in the geologic record. And moving, as you can see, we've gone from huge, big, medium, small. Now we're getting real tiny. But if everybody likes Pompelli's rule, where structural geology kind of replicates itself at all scales, we're now looking at this sample under a photomicrograph thin section. So this is transmitted cross-polarized light, and you can see almost the same geometry that I've highlighted in blue on this thin section. Those are fault slips. You see the same similar growth geometry at this scale that you see almost at the basin scale. So it's a kind of a fun activity doing this at all scales and the same age relationships. We're not going to go into details of this. This is a whole manuscript in itself. The main feature is from thin sections of these micro slip events, we're able to document that there's at least 6 significant ruptures preserved during precipitation of these banded veins. And we're just going to look at 2 of them. The youngest one, which you can see up here in this white box of D and E, highlighted blue. This is the final rupture event. That little tip is propagating through band 4. And I did make a mention of it. Band 4, 3, 2, and 1 are the main microcrystalline adularia bands that host the visible gold and silver. The final little fault tip is in the photomicrograph at the right, reflected light. What we're actually seeing is the very tip of that microstructure as it propagated up. Hopefully everybody's seen my hands. I talk with my hands a lot. Propagating through that final mineralized band. You see the adularia electrum, the little growth, and one can argue the little fractal dendrites forming. But that tip started out where these two surfaces of contact 6 were touching, propagated up as these 3 little microbands were precipitating out, and died by the time you got to the next massive quartz band. So this is an individual little micro rupture, little microseismic event that was coeval with precipitation of these mineralized bands. The next one we're going to look at is at the base of this fault, and just like you'd see at the basin scale, you go down dip to the oldest portion of the structure, you should have a cross-cutting relationship series of overprinting tectonic events showing the cumulative slip history of this structure. And that's indeed the case. If we look within this teal box, we see evidence of multiple ruptures on this structure. So this is that teal box. This is on SEM using cathodoluminescence. This kind of opaque black and gray is the quartz ground mass. That's just the non-tectonic portion of the vein. One of those fault slips is highlighted here in light blue. The whole little fault zone here, largely with the calcite laths. The other side of the fault, there's an actual horse block. Then off the actual image, this is the total width the SEM could capture. There's another little fault zone to the right. And the neat thing here is we actually do have cross-cutting relationships suggesting that there's at least 6 slip events preserved in this micro fault at the base of the structure. The first one is actually shearing off asperities on the sides of the structure. Then you're actually rotating calcite laths to be in the lowest strain direction, so no different than imbrication of clasts in a stream. Then we can look and zoom in a closer detail and see subsequent brittle events preserved in this fault zone. In this block number 1, we're actually seeing intergranular microcracks breaking through the quartz ground mass. Actually, you can see it breaking up this calcite lath and a tip. So that takes at least 3 events. And if you zoom in on one of these calcite laths, this is probably the neater texture, you're actually having intergranular shear failure. You're actually causing, in this case, a dextral slip, which mimics the actual slip across the fault zone, shearing across the cleavage planes within the calcite lath. So the lath is being oriented within a fault zone that's already been established, then you're shearing the calcite itself. So it's actually 4 slip events to get to that stage. And the last little fun photo to look at is within this adularia grain. Number 3, if you look closely over here to the right of it, you're actually creating a little micronormal fault that's down dropping this hanging wall sidewall to the footwall, and this transgranular microcrack goes from the quartz into the adularia. So this sample is indeed preserving multiple ruptures of the host fault. Pretty neat. Ultimately, the whole story, the implications are is we're seeing a multi-scalar record of co-seismic or co-tectonic permeability influencing where and when hydrothermal fluids will flow in the basin environment to form these deposits. And the real takeaway is that permeability is short-lived. It's transient. That's going back to McCrogg and Hronsky. These are transient events. On the crustal scale, this is really represented by the 3 million years of magmatism associated with Northern Nevada Rift. And the very short hydrothermal transient event is only roughly 100 to 200,000 years during that 5 million year window. And the fun thing is this project, we focused in on that couple 100,000 year window. We're able to tie that syntectonic nature of hydrothermal activity to individual events. At the deposit scale, being roughly 100,000 years, you had a very critical stage in basin development where fluids were coming up to form the deposits, and that relates back to the apex region on the western margin. Then those bands themselves are actually recording the recurrence interval of large earthquakes at roughly 20,000 years. And that band history we see in the photomicrograph is actually preserving that peak in coseismic permeability. If we just did the rough numbers, that would last for about 3,000 years post-rupture. Then we have the interseismic period where that healing occurs, where you get more or less the barren, dead calcite and quartz in between those mineralized bands, kind of representing the interseismic healing period during this ore forming episode. And to tie it up, going back to this is a fun part. We see this preserved on the larger scale, and it's exposed. That's the best part in geology, is seeing what you want to see in the cross section, but actually going out and be able to visualize it in the field. So this is the Cortez Range looking to the south again. Southeast is over here. Top of the range is this surface up here where we have the Miocene basalts. Oranges are Eocene and Miocene sediments. Then Paleozoic basement going down roughly 1 kilometer beneath that Miocene paleosurface. And that's what we're showing with the dashed lines. So we're really getting a proxy for the upper component of this model from Simmons. Well, we're also seeing how this relates to the basin. So on the Cortez Range, we really have a beautiful cross-section that I'm kind of approximating by the schematic, but I'll tie the actual mappable faults to the schematic cross-section. And this is the geometry you're seeing out there. It is this juvenile half-graben geometry. And each one of these faults can be tied to either epithermal mineralization, Miocene age, or in some cases tied to Eocene Carlin mineralization. This basin represents that primary deformation zone of the whole rift. So that corridor that is experiencing the greatest amount of strain. We see that preserved in the record by that degree of extension. The largest scale, we saw 4% just across the Miocene paleosurface from heave on those faults. The dikes, we see focus strain on discrete corridors associated with the rift that are associated with the western margin where the highest displacement faults are. And we see how that is focused in the shallow environment to the apex region of the Ryder Block where Fire Creek, Mule Canyon, Buckhorn, and all the epithermal deposits form. And we're really just seeing a geologic record of the preserved strain partitioning across the basin. This is just me visualizing it. If you think of each structural level of that cross section, this is how strain is being partitioned across the whole basin. So instead of thinking of this whole deformation zone as a rubber band being pulled at the ends and stretching it out, you're really pinching it right in the middle, and the whole band is being pulled apart, but almost all that stretching is occurring between your fingers. And that's where you're going to allow the basalts to ascend to the surface to feed the flows, as well as the hydrothermal fluids. So that rupture of those largest displacement faults at depth, the brittle ductile transition, opens up that barrier, allowing fluids to ascend. First time this happens is in the late Eocene. Eocene age hydrothermal fluids follow the same pathways that the Miocene fluids did, form Carlin-style deposits, albeit at different depths due to reaction with carbonate rocks. The Miocene fluids later did. And the neat thing here is those dikes actually preserve the geometries of these pathways. So that's late Eocene. Miocene, as we mentioned, was kind of a boring period as far as the subsurface and ore deposit formation was going on. But a lot of things were happening on the surface as far as mammalian evolution. Then the mid-Miocene showed up. The basin got filled with more volcanics. The same faults rupture, large earthquakes, cause the permeability to reopen from depth to the surface. Now those fluids migrate up to the Miocene paleosurface to form epithermal deposits. And this is all preserved beautifully in the Cortez Range. So to tie it up, the project identified favorable sink environment, the structural geometries, fertile source, looking at those magmas at depth. Then the main barrier to overcome is having the event avalanches of the proper scale faults to actually allow permeability all the way through the crust. And only when all three of these things overlap in space and time are you capable of forming a deposit. And when you have just two of the three, you kind of get one of these other systems. Ultimately, for the benefit of this project, you need preservation, and we have great preservation and actually exhumation of the system to actually see all this in outcrop. So that is it. I would be remiss not to thank the large group of people who made this possible. I went back to graduate school in the same time window of getting married and starting a family. So a lot of family helped out making this happen, a lot of industry support and academic support from a large group of people. So thank you very much. Happy to take any questions.